Okay, maybe it's a good moment to get started. So if you thought that things were technical earlier, it's going to get a lot worse today. So today I'm going to discuss the L2 extension theorem. Okay, so one of the important things about these kinds of theorems is that we really do want to have them with singular Hermitian metrics. We've seen singular Hermitian metrics here and there, but I haven't really discussed their definition, for instance. So let me just say a few quick words about singular Hermitian metrics. So the first thing is that these are so far only defined for holomorphic line bundles, which is to say, that's the key word is line, which is to say that we can give a definition of singular Hermitian metric for vector bundles, but it's, at the moment, we don't have one that we can actually do anything useful with. So I'm going to stick to line bundles, and let me tell you the definition. So the definition, so singular Hermitian metric is sometimes abbreviated SHM. So it's a metric, but it's only a measurable metric a priori. So is a measurable metric. What do I mean by that? It's a measurable section of L star tensor L star bar. So we discussed early on how metrics are sections of this bundle because you feed in a vector in L and a conjugate vector in L to this entry. Okay? So you can talk about measurable sections, that's the advantage, but this we can do for a vector bundle as well. The next thing is the important thing. So such that for any holomorphic frame, actually you can say smooth frame, but I'll just say holomorphic since we have them, say C of L, you get a function, let's call it phi C. So this is a negative logarithm of h of C. In other words, h of C is e to the minus phi C. Okay, so we want this function, so the function is L1 loc on the domain where the frame is defined. Okay? And the point of this is when you have an L1 log function, it's a distribution. So you can differentiate it. And so the 1,1 current, dd bar phi C, and this current is independent of Xi. Frame that you choose is called the curvature current of H. So if H were a smooth metric, then this would be exactly the curvature 1,1 form. Okay? Since it's a line bundle, the endomorphisms of the line bundle is just the trivial bundle. It's a L tensor L star. That's a trivial bundle because it has a global section given by the identity map. So, okay. So, yes? Yes. This is H here. So this is, should be familiar by now that if H were a smooth metric, then this would be exactly its curvature. Okay? But now it's not a form anymore, it's a current. The crucial thing, so crucial in using these is the ability to approximate them. Approximate such H by smooth HJ, smooth metrics of the line bundle, which increase monotonically to H, and such that the curvature of the corresponding smoothed guy. So let me just use this notation since it's independent of the frame anyway. Okay, such that dd bar j is no less positive than the current dd bar phi. So you can make sense of the positivity of currents, and a smooth form is in particular a current via multiplication. So you're just saying that dd bar phi minus dd bar phi j, dd bar phi j minus dd bar phi is greater than or equal to 0. Yeah. So in particular, if you have a positively curved thing, see the monotonicity of hj reverses for phi j. So because it's e to the minus phi, it goes the other way. So you have a decreasing family of, if you have positive curvature, plurisubharmonic functions, and a decreasing family of plurisubharmonic functions always converges to a plurisubharmonic function unless it goes identically to minus infinity, which won't happen to us. So, okay, so that's the principle, and that's about, okay, so the thing is that you cannot always do this approximation, and that's a serious problem in complex geometry, for example, of Kähler manifolds. So on a compact Kähler manifold, you cannot do this. But one non-trivial, it's rather deep fact, is that you can do this on Stein manifolds. So possible to do this approximation on Stein manifolds. So that means that you have this tool on Stein manifolds, but you also, if you're doing L2 theory, you also have the tool on projective manifolds. A projective manifold, a submanifold of projective space, has the following interesting property. You can remove a hypersurface from it, and the resulting manifold will be a closed submanifold of Cn. So that hypersurface is, so if you're in a projective space, here's your projective space, say some Pn, and you have your manifold X. This Pn has a lot of Pn minus 1s, just hyperplanes, just zero sets of linear functions. So you can take one, some Pn minus 1, just a straight subspace, and then if you remove this intersection, you know, this, for example, you could take the coordinate z0. If you look at the chart where z0 is non-zero, that's a copy of Cn, and your manifold is automatically embedded in there as long as this hyperplane meets the submanifold transversely. Okay? And by Sard's theorem, you can choose this hyperplane generically so that it does meet transversely. So, and then, of course, you can perform various calculations, construct some holomorphic section. If that section is in L2, then it cannot acquire a singularity at this point. Oh, this is actually not a point, but it's a hyperplane. Okay, you cannot acquire a singularity Because if you did, it would have to be a pole, so it would have to be something that whose denominator vanishes along this thing. And then when you look at the L2 condition, you see that's never integrable. So the L2 condition also eliminates the poles and allows you, by Riemann removable singularity, to extend your section across this piece. So it's an extremely useful tool in algebraic geometry, these singular metrics, via this Bombieri trick, which we've used 1,000,000 times by now. So, okay, so that's a kind of enough to say about singular metrics. I'm going to use them as though they're smooth metrics. And if you feel tense about that, just believe that in Hörmander's theorem, you can regularize the metric, smooth it out, construct your section, and take limits to get, for example, when you have something in L2 which is smooth and satisfies a finiteness condition, then it must vanish on the singular locus. Okay, so this is the trick we've used in various problems and different points in the lecture. Okay, next thing I want to talk about is something called adjunction. So, adjunction is a way of relating, a way of understanding the normal bundle of a smooth hypersurface in a manifold. So here, this X will be some complex manifold. And let's say that Z in X is a smooth, complex hypersurface. Okay. So we talked early on when we were giving examples of line bundles, we talked about how such a thing defines a holomorphic line bundle. Let me just remind you of this, how you get this. So the way you get it is you find functions Tj holomorphic on some open set Uj such that Tj equal to 0 is exactly Z intersect Uj. And then the line bundle is given by the transition functions Gij is Ti over Tj. All right, so once you have those transition functions, you can define a line bundle, but also if you write this as Ti is Gij Tj, then you get a holomorphic section T along with this. And this holomorphic section has the additional nice property that the zero locus counting multiplicity is exactly Z. Okay? So here you have to assume that the dTj is non-zero, nowhere zero. And you can do that because it's a smooth manifold. It's just the implicit function theorem, basically. Okay. So now what I want to do is something that may look strange. I want to apply the exterior derivative to this here. So I get T dTi is Gij dTj plus Gij dTj. And I can do this because I'm working locally. These are just holomorphic functions. But you remember in the very beginning when I introduced connections, I said that there was a kind of problem term that you get, which makes this not behave as a section of the line bundle. And it's exactly here. So if it were a section of the line bundle, you would only have this term. But you have this additional, oops, that was impressive display of calculus. Excuse me. This second term here is exactly what causes the problems. And usually you remove it by defining a connection. And there are many choices, but I'm not going down that road now. Now I'm going to do something a bit more spectacular. I'm going to restrict this relation to Z. So if you restrict to Z, then this Tj vanishes. Right? So you get dTi is Gij dTj. However, so this now looks like a section of L, except that it's not a function anymore, it's a one form. So now it's actually a section of this vector bundle, L tensor T star of X, restricted to Z. So, but actually, it looks like a an object which has many components. You know, it looks like a general vector, but in fact, it's more special than that. This one form has an additional property, which is that it annihilates the tangent space of Z. Right? So the Z is defined as a level set, so that means that the differential annihilates every tangent vector to Z. In other words, it's an element of something called the conormal bundle, which is the annihilator of the tangent bundle. So in fact, you get a section dt, which is a holomorphic section just along Z of the line bundle L tensor with the dual of the normal bundle on X and Z, modulo Z. So this just means what I said. It's one forms that annihilate the tangent space of Z. So in algebraic geometry, the normal bundle is not a well-defined thing. It's a well-defined in the sense that it's the dual of the conormal bundle, but it's not an actual sub-bundle of the tangent bundle until you introduce some extra data. Like you need a metric to talk about what orthogonality means. Once you know that, then you get a realization of this bundle, but naturally it's defined as an abstract line bundle on the hypersurface. Okay, there's one last additional feature. So up to here, I've not used the smoothness anywhere. I mean, it's the set of all one forms which annihilate the tangent bundle to Z. Right, so I mean, I said here that these dtj are nowhere zero, but I haven't used it anywhere in the discussion up till now, right? So in fact, this all makes sense just fine, even if up to here, everything makes sense just fine, even if this is a singular variety. But then you don't have a notion of the conormal bundle anymore. So this is some section of something, but it's not the conormal bundle. But if you assume that the hypersurface is smooth, then this really is the conormal bundle. But there's one additional feature. This section has no zeros anywhere. Okay. What does that mean about this line bundle? This should say L sub Z. It's trivial, right? So this LZ tensor n x mod z star is trivial. So this is on Z. It's only defined on Z at the moment. However, so what this means is that L is isomorphic to the dual of n star, which is called the normal bundle, right? This abstract. So L is isomorphic to the dual of n star. So it should be star star, but that's what we call the normal bundle. Okay. So notice that the normal LZ. Sorry, I keep forgetting the Z. So notice the normal bundle is only defined on Z, but LZ is defined on all of X. So adjunction means that for a smooth hypersurface, there's an extension of the normal bundle as a holomorphic line bundle on the whole manifold. That's a remarkable feature. We're not going to use that very explicitly, but we're going to use it in two different ways. First of all, we're going to need this section. So, but then we're also going to use the structure here. So if you think about, for example, of how you compute volumes in the manifold, so near, say, in an epsilon neighborhood of some point of Z, in an epsilon neighborhood of a point of Z, you have the volume form for Z, dV sub omega sub G, if you have a metric G. So you have the volume form, but that should, so that equals roughly epsilon squared times, so dt wedge dt bar maybe I should write it like this. This is what I mean to say. So this dt can serve as a differential of a coordinate in some sense. The dtj are give you coordinates in the direction which is transverse or perpendicular, hypothetically, to z. Okay, so that means that you can write the volume form dvg as some volume form on z. So let me remind you, this is the metric form to the power n divided by n factorial. This is the metric form to the power n minus 1 divided by n minus 1 factorial, because you're in a hypersurface. So now, if you divide this by epsilon squared near z and let epsilon go to 0, what do you get? Well, you get this divided by the length of dt squared. Except that this is now, it looks like a metric, so you need to add in some metric for, let me just leave it like this, leave this in quotes. You'll see this popping up in the proof of the L2 extension theorem. Okay, so it's longer than I wanted it to take. But.
In the construction of this line number, when you choose open sets, what do you choose PGW when usually does not intersect that?
Doesn't matter. You take your favorite pick.
Just any
doesn't matter. Whatever you like. Yeah. It doesn't really matter because it's a line bundle. So if you make one choice, it doesn't mean anything. It means that you made it with respect to a certain frame. If you make another choice, the frame will be scaled by the previous frame, and this function will be inversely scaled by the same thing. So there's no way to say what it should be, so take your favorite. Okay, let's get started on the L2 extension theorem then. Okay, so, let me just state the thing. I should say there are many L2 extension theorems. This one is for hypersurface. There are versions for higher codimension, but they're not as precise. Yes? Sure.
Is the unique extension that exhibits for the normal bundle process, or
yes.
This is the unique
This is it. Yeah. I mean, well, I'm not sure how to answer that. On a compact manifold, yes. You could imagine a line bundle which is trivial on Z, but maybe not globally trivial. And then you could tensor with that. That could happen too, I guess. So anyway, it's not important if it's unique. It's important that there exists an extension of the normal bundle. Yeah. Question? Just some metric for defining the volume. It doesn't matter. It's the same metric on the two sides. That's the important thing. So this one, you're taking this metric, basically the determinant of this metric, that's in n dimensions. This one is the determinant in n minus 1 dimensions of the inverse, right? It's the metric on the cotangent bundle. And then you're dividing by the norm of G, so it scales correctly. Anyway, it's an exercise in calculus. It's the Jacobian formula for applying Fubini's theorem. So, yeah. No, I'm dividing by epsilon squared. So the dV has a maybe it's not exactly right, so I guess it should be the area of the cross section. So it's epsilon squared times the area of the cross section. That depends on T as well. So, I kind of botched this. You'll see it in the formula and you'll see what I mean. So it's going to be a while though. Okay, so as I was saying, there are a bunch of L2 extension theorems, but I'm going to state one, which I proved some years ago, but is probably basically known. I just didn't know at the time. Okay, but it's a very precise form. So, okay. So now let's let X is going to be a Stein manifold. And then we have a line bundle. I'm not going to say holomorphic line bundle, but all my line bundles are holomorphic with some metric, which I'm now going to write e to the minus phi instead of h. So this is just a metric for L. Then I have Z, a smooth hypersurface. By the way, smooth can be removed with some effort, but let's not worry about it. And then we have the line bundle LZ, and then we have a section T for it, which we just defined, right? And then I'm going to assume there exists a metric, and I'm going to call it e to the minus lambda for LZ, such that, and now they're going to be two properties of this metric. The first one is that if you compute the pointwise norm of this section with respect to this metric, and you take the supremum over all of x, that's less than or equal to 1. And the second thing is a hypothesis. Now remember, this e to the minus lambda is a metric for LZ, and you should think of LZ as the normal bundle of the hypersurface. So I need to say something about the curvature of the hypersurface relative to the curvature of the metric, and that's what the next hypothesis is going to be. It's dd bar phi. Oh, I forgot one thing. I'm going to fix a Kähler metric. G. Kähler metric. Okay, so dd bar phi plus this Ricci curvature of G is greater than or equal to 1 plus delta times, I don't know, C times the curvature of lambda, or e to the minus lambda, so for all C between 0 and 1. So it's a convex combination of dd bar phi plus the Ricci of G minus dd bar lambda, and dd bar phi plus the Ricci of G minus 1 plus delta dd bar lambda. So it's equivalent to say that just those two are positive. I'm going to say it like this. Okay, and here, where delta is some positive number, which is part of the data. Okay, so it's some fixed number. You're assuming that there exists some delta. The delta will appear in the statement of the theorem as well. Okay, so then the conclusion is that for every holomorphic section of L, not LZ, but L, along Z, such that the integral of f squared e to the minus phi dAg over dt squared g e to the minus lambda is finite. So this is the volume form you get in this as in the limit as x collapses onto z. But don't worry, this is just something that comes out in the proof. So if you have every such section, there exists a section of L on all of x such that f restricted to z is little f and the usual L2 norm of F. So this would be h of ff in our previous language. I'm just writing this as e to the minus phi, but it's still a metric. Okay? This will be less than or equal to 24. Oh, I need a hypothesis on this delta. So it's bigger than 0, but it shouldn't be more than 1. This is unfortunately a product of this particular method. So then there's a constant, 24 pi over delta times the integral over z of f squared e to the minus phi dag over dt squared g e to the minus lambda. So this is the L2 extension theorem. Now let's try to prove it in half an hour. Proof is rather long. I'm going to be a little fast in some of the parts because I want to finish. The details are in the notes, though. So if it works for some t and some lambda, then for any other t, there's a lambda. So that's something to get used to with the line bundles, is this scale invariance of the language. So, sorry? You want to know what it means geometrically? Is that your question? Oh. Well, okay, so by the way, I defined Ricci a few times. You take the volume form and think of it as e to the minus some function times the Lebesgue measure in local coordinates, and it's dd bar of that function in the exponent. That is the Ricci curvature. Geometrically, this says something like this. It says, so first of all, this convex combination is because you may not be able to find dd bar lambda, which is positive. If dd bar lambda is positive, you can just do this for c equal to 1. So dd bar lambda is carrying some kind of global effect on x of how z is curved inside x. So it means that it occupies a certain amount of mass inside x. And that mass is sort of measured by the set of holomorphic sections that are L2. So that's a measure of energy, which is sort of the mass of this Z. And then what you want is to extend it to a global data. And this statement says that in order to do that, the geometry of L on X has to have more mass in the total space than the curvature of Z. Strictly more. That's what this delta is. So if delta goes to 0, then you end up getting not enough mass to solve the extension problem, and then it may or may not be solvable. Certainly not with this estimate. That's the meaning. It's not at all obvious from the statement or the proof.
So there are two line bundles.
There are two line bundles. Really, there's only L. The point is that L, I mean, they're only extending sections of L. But LZ is the line bundle that's measuring the curvature of Z inside X. Okay? Okay, I have some exercises. Unfortunately, they're not easy, because the theorem's not easy. And one of them has 7 parts, but that 7-part exercise, if you solve it, you will understand this theorem much better. Also, the exercise is like a baby version of Pingali's talk in the afternoon, so it'll also help you digest that one. Okay, so let's get started here. So first of all, so X is Stein, so we can take an exhaustion of X. So there exists omega j, so the relatively compact subdomains of X, which are also Stein. They're pseudoconvex domains, so that means they're Stein. Strictly pseudoconvex exhaustion, such that their union, omega j is all of x. So now what we're going to do is try to solve the extension problem on omega j for f, little f restricted to omega j. And then we'll take some kind of weak star compact limit to get the extension on x. So let's just fix once and for all the section to be extended. So because it's a section of a complex submanifold in a Stein manifold, there actually exists a holomorphic extension to the whole Stein manifold. So there exists f in gamma O, let's call it f0 in gamma O of xl, such that f0 restricted to z is f. But unfortunately, it's not L2 with respect, or we don't know that it's L2 with respect to this L2 norm. Okay. It's L2, okay, so maybe I should say just a quick word. We solved this problem when the line bundle L is trivial. That was the content of yesterday's talk. So you can see it as an exercise to modify for a non-trivial line bundle. But if you understood the philosophy, there's no difference. Okay, so therefore this is not an L2, but in fact, oh, and there's another thing I need to say. So I'm actually, in this theorem, the metrics are singular, but I'm actually going to assume that they're all smooth. Okay? At the end, with this monotonicity of approximation, I can pass the limit again by some weak star compactness techniques. So I'm just going to assume the metrics are smooth. All right? Okay, so then because they're smooth, if you take this f0, and integrate it, compute its L2 norm on this compact subset, this is going to be finite. Okay. But the norm a priori depends on j. So we don't know that there's something independent of j. If we did, we would be more than halfway to proving this theorem. So we can't assume that. Okay, so now what we want to do is modify this f0. So goal, modify f0 to some f. Another extension with good estimates. In other words, with the right L2 norm. Okay, so this is by now relatively routine. We've seen it done in a bunch of different ways, but we have to do it carefully here. So we're going to use this cutoff and correction with d bar, but the d bar won't be enough. We're going to need the Donnelly, Pfefferman, Osawa estimates for the correction. Okay. All right. So the cutoff. Okay. So let's take some chi, which is compactly supported on the interval closed at 0, open at 1, and I extended by 0 to all of r. And I don't want to say that, but you know that I don't want to write it, but I said it. We want the values to be less than or equal to 1. I want it to actually be monotonic decreasing, but that's not as important as, so chi should be identically 1 on some interval 0t, where this number t is some number less than 1. Eventually, I'm going to let t go to 0. And then I want the derivative I prime to be less than or equal to 1 plus c times t. So for some constant c, which will have to be bigger than 1. So the point is, so if you have here 0, here's 1, here's t, you go 1 up to here, and then you smoothly get an almost straight line, just smooth it at the ends. The derivative is always, at most, what it is in this linear part, and that's roughly 1 over t. Yeah. 1 over 1 minus t, right? But if t is small, then there's going to be, maybe make this t less than a half. Then you can have some c. C will probably have to be a little bit bigger than 2, but you can always arrange this slope. It's just slightly bigger than 1. Okay? Okay. And then, of course, our extension is, we're going to have a smooth extension, which will be, oh, and let me define chi epsilon to be mod t squared e to the minus lambda over epsilon squared. So I'm using here the fact that this is less than 1. Okay. So I get this cutoff function. Chi of that, thank you. Chi of that. And so I take chi epsilon and multiply it by f0. Of course, this is not holomorphic. It's a smooth section, but it's actually holomorphic on a neighborhood of z, because the set t equals 0 is z. So something like on a neighborhood of the size t epsilon, we're going to get a holomorphic section. Okay. So this is some smooth section, omega I, L. So it's supported very near Z. Okay. And then the error from holomorphicity, that's just d bar of this f tilde epsilon. This is the error from O membership. So it's close, but actually this derivative is huge. So when you differentiate this, you're going to get a factor of 1 over epsilon in size. Okay? Okay, let me remind you of the Donnelly-Pfefferman-Osawa estimate. So this is going to be a version for 0-1 form and singular Hermitian metric. Okay. So let's let e to the minus psi be a singular Hermitian metric for the line bundle L restricted to omega j. And now let's take eta, some C infinity real valued function on x. This function eta appeared in the Donnelly-Pfefferman estimates. And then this a should be some positive function. So let's say from 0 to infinity. This is some positive function. But in this case, so in the Donnelly-Pfefferman estimates, you just can assume positivity. But here we're going to need it to be at least continuous. But in fact, our choice of a will be smooth. We need this to be continuous. And now the positivity hypothesis, I will remind you, is that this form, this endomorphism C, which is e to the minus eta times the curvature of e to the minus c, that's dd bar of c, it's a current, right? And then plus, this is not a reminder because we worked with nq forms. If you work with 0q forms, you have to add this term, getting a metric for the anti-canonical bundle from the volume form. This is the curvature of that metric. So this is an induced curvature on 0q forms. And then we had this twisted term, dd bar eta minus 1 plus a over a d eta wedge d bar eta. Okay. So now this is a current, so we can certainly say that it's positive, but in the L2 estimates, it will be difficult to measure the norm with respect to the inverse of this current, right? So we don't want to do that. So instead, we just want to say that it's greater than or equal to some smooth, so this is smooth 1-1 form in this case. Right, so usually it would be an endomorphism of the vector bundle, but since these are line bundles, the endomorphism is just the identity. And this thing should just be greater than or equal to 0. So you can't invert something that's not positive definite, but it's not too important whether or not this is positive definite. It's more important whether or not the form you have has a finite integral. And in our case, you'll see that appearing. So under this assumption, the conclusion of DFO is that so for all L restricted to omega j valued 0, 1 forms phi such that so d bar of phi, this is S of phi, but it's the same as d bar of phi equals 0. And now you'll see this form theta appearing. And it has a finite L2 norm with respect to this metric theta. So now the metric G is not going to be here, okay, because the Q is 1. Because I'm using theta instead of G, excuse me. There exists some U, which is a section of omega j, L restricted to omega j, such that the twisted d bar equation with data phi is solved by U. And you have the estimate, integral over x, omega j, of U squared e to the minus phi dv sub g e to the minus psi. dv sub g is less than or equal to this thing. Okay, so this is what we went through. The only difference, the only serious difference here is that this psi is singular. Okay, so in particular, if it's singular enough, then because this A is continuous, the solution U will also be continuous. Maybe we need C1, but anyway, it's going to be smooth. So this solution U will be continuous, and so if you have, in particular, it's defined everywhere. And so if this integral is finite, this will force U to vanish along the singular locus of psi. Okay, so now the art portion of the proof. This is where your mind could get blown. So it involves the choice of psi, eta, and A. First of all, psi. Psi will be the metric phi, so these are the exponents of the metrics. It will be phi plus the log of this function. So let me point out that dd bar psi plus Ricci of g, right? That's dd bar phi minus dd bar lambda plus dd bar log mod t squared. That's positive, so I'm going to ignore that. Right? This is going to be greater than or equal to 0 and greater than or equal to delta dd bar lambda. Okay? So because there's this, basically psi is phi minus lambda, so if phi satisfies those conditions, then psi satisfies these. Okay? Okay, I'll need some auxiliary functions to make the formulas slightly more digestible. So I'm going to just write V for log mod t squared e to the minus lambda. And so, in other words, e to the minus v is mod t squared e to the minus lambda. And you should think of this as the absolute value squared of the function that cuts out z, okay, in what I'm going to do. So this is the logarithm of the absolute value squared of the function that cuts out z. So this is some function from x to, and it could be minus infinity. In fact, it's minus infinity along z. But it's no bigger than 0. And then the other auxiliary function I'm going to need is s, which is gamma. Gamma is a constant, minus delta log e to the v plus epsilon squared, where this gamma is going to be 1 plus delta log 1 plus epsilon squared. So e to the v is less than or equal to 1. So that means that this function s is greater than or equal to 1. Okay, so now the function eta. You're going to love this one. This is negative log of 2 plus log of 2e to the s minus 1 minus 1. Let me introduce yet another auxiliary thing. Let me call what's inside this logarithm h of s. So this is negative log h of s. Epsilon is some fixed number. It's the same epsilon that we had in the cutoff. Yeah. Okay. Okay, so now let's just compute dd bar eta minus 1 plus a over a d eta wedge d bar eta. I haven't told you what a is yet. I'm going to choose it based on this computation. Okay, so in fact, I don't have enough time to go through this, but this is an exercise in calculus. I'll let you check that this is h prime of s over hs times negative dd bar s minus 1 over a h of s times h double prime of s times a plus h prime of s squared over h of s. Okay? So now I'm actually going to choose a so that this term here is 0. So that's why the letter a is used, is a stands for absorption. It absorbs some of the complicated part of this Donnelly-Pfefferman-Osawa twist. Okay? So we take a to be negative h prime of s over h double prime of s times h of s. Okay, so this h, you have to verify these properties, but h is at least 1, and h double prime is negative. So that's good because this a has to be positive. If you remember how a came about, it came from the Cauchy-Schwarz inequality with the big constant, small constant. So that always has to be positive. But this function is positive because h double prime is negative. Okay. H prime is not negative. So that's a little tricky to make an increasing function which is concave. And that's part of the geometric constraint of this problem. That's why you need a little bit of art here. Why does it work? Okay, so first of all, this function looks very complicated, but if you really look at it carefully, it's just negative log s, more or less. Okay? And that negative log s, or maybe it's better to think of negative log of s, okay? E to the s. So e to the s is a relevant function here. Sorry? Squared. All right. Let me just make sure of that. It is squared. Yeah, sorry, you're right. So anyway, all I was going to say is that this negative log function was one that we had in one of the exercises, and it shows that the punctured disk has a function with self-bounded gradient. This function is modeled after the function in the punctured disk. And if S were really straight, then you could really get very close to that very same function. But because this S is curved, the curvature of S causes some problems. And so you basically have to try to, pull the rug to the corner of the room because it's not covering the floor, and then you worry that maybe it won't cover the other corner. It just turns out that the rug fits. That's the only way I can explain how I came up with these things. So it was really just playing around until the estimates worked. So I wish I had a better answer. And at the end of the course, I'll give you another proof of this theorem, completely different, that's more convincing in terms of the content of the proof itself. But this was just really just playing with functions until it works. There's many moving parts, and we've only seen some of them. So just having this is not enough to be convinced the proof is going to work. I'm going to go over time, because I don't want to spread this into 2 lectures. And so it'll cut into your problem session a little bit, but sorry about that. I'd rather explain it than go way too fast. It's already too fast. So. Okay. There are some features of this function, so important properties. Let me say that h is greater than or equal to 1, h prime is greater than or equal to 1, and h double prime is negative. We already discussed that one. I said h prime bigger than 1 as a problem here, but it's obviously not. It comes up elsewhere where you need h prime to be positive. You'll see in a moment. So yeah, we can forget about that too. We're in it for the long haul here, folks. Okay, so let's compute. What is negative dd bar of S? So this is going to be delta, negative dd bar of S is delta dd bar log e to the v plus epsilon squared. And here there's still some clever calculating. So you have to, again, this is partly reverse engineered. So it's e to the v d bar v over e to the v plus epsilon squared. And so this is going to be delta e to the v over e to the v plus epsilon squared dd bar v. This is an important term. And we have to deal with the rest. So now you're going to have to apply d to this thing here, and it's a calculation. I'm going to tell you the outcome. And I'll try this. I hope you'll see later why I wrote it in the way that I did. But this is d of e to the v over 2, wedge d bar e to the v over 2 divided by e to the v over 2 squared plus epsilon squared squared. So that's what you get. So it's this d of e to the v over 2, which looks a little funny, but you should think of e to the v over 2 as the function which cuts out z. So I'm taking d wedge d bar. It's like the area measure. That's why it's like that. Okay, so now let's put in what v is. So this is going to be so delta e to the v over e to the v plus epsilon squared. And then you're going to have dd bar log mod t squared minus dd bar lambda, and plus this same thing. So delta 4 epsilon squared, d e to the v over 2 wedge d bar, e to the v over 2 divided by e to the v plus epsilon squared squared. Okay, so now if you look at this for a moment, so dd bar log mod t squared, that's actually 0 outside of z, and it's some multiple of the current of integration of z. That's called the Poincaré-Lalonde formula. But we don't care about that formula here. The only thing we care about is that this function e to the v actually vanishes on z. Okay, so when you multiply this smooth function by this compactly supported current, you get 0. Okay, so So this term goes away. So that's what we have left there, okay? So now, I need this DFO. So I'm running out of space. Okay, you have to try to remember what this psi is. Okay, so then this calculation implies that dd bar psi plus the Ricci of G plus dd bar eta minus 1 plus a over a d eta, which d bar eta, so that's equal to dd bar c plus Ricci of G plus h prime of s over h of s negative dd bar of s. We computed what negative dd bar of s is. It's this quantity here. So I'm just going to use that in the computation. But then I'm also going to, so this term here, it's positive, but you have to be a little careful because, well, let me just write it down. Okay, you can confirm this is just algebra. So this is going to equal 1 minus h prime of s over h of s e to the v over e to the v plus epsilon squared. There is a reason to why I'm writing all these crazy formulas down. So d bar psi plus Ricci of G, and then plus h prime of s over h of s e to the v over e to the v plus epsilon squared, dd bar c plus Ricci of G minus delta dd bar lambda. Okay? And then there's the last term, this plus delta times 4 epsilon squared, d of e to the v over 2, wedge d bar e to the v over 2, divided by e to the v plus epsilon squared. Okay? Now, remember I told you to notice that the curvature conditions on phi exactly mean that these two terms are non-negative. So the properties of H are such that this coefficient is non-negative and this one is non-negative. So this H prime being positive, for instance, is enough for that. So that's something you have to check, but it's true. So this was part of the adjustment in constructing these functions. It's necessary to have this expression positive. So then the whole thing, so it just means at the end that this, we can scratch this whole piece out, and that quantity is greater than or equal to this times h, oh, I'm sorry, there's a missing h of s over h prime of s. It comes from this factor here. Okay? Now, oh, oops, h prime of s over h of s, excuse me. So this h of s is e to the minus eta. Okay? So that means that this exactly implies that psi is greater than or equal to delta times 4 epsilon squared d e to the v over 2 wedge d bar e to the v over 2 divided by e to the v plus epsilon squared. So now we can apply Donnelly-Pfefferman to any form whose L2 norm with respect to this measure is 0. But notice that this measure vanishes on all directions that are not transverse to z in some sense. This is the defining function for z, is how you want to think about it. So very few differential forms will actually have a finite L2 norm with respect to this theta. But luckily our alpha sub epsilon is one of those forms. I think I erased alpha sub epsilon now, but now I can need 7 boards for this proof. remember our form alpha sub epsilon, this was d bar of chi of e to the v over epsilon squared. Now we can express it in terms of this e to the v times f0. F0 is holomorphic, so d bar doesn't act on it. So this is equal to chi prime of e to the v over epsilon squared times d bar of e to the v over epsilon squared f0. And now I'm going to write this as chi prime e to the v over epsilon squared. And this will be 2 e to the v over 2 d bar e to the v over 2 divided by epsilon squared f0. So just think of e to the v as e to the v over 2 squared and apply the chain rule. Okay. So what does that mean about that? You see, so now you can see that this form is just a multiple of this d bar of e to the v over 2, which means that with respect to that theta, it's going to be well defined to invert the theta. So they're going in the same direction. So what this means is that alpha epsilon squared theta e to the minus psi is equal to 1 over delta epsilon to the 6th, this has to get squared, chi prime e to the v over epsilon squared, squared f0 squared e to the minus psi, then this e to the v over 2 gets squared, so e to the v, and then you're supposed to divide by this norm. So let me just write out the now that's fine. And then e to the v plus epsilon squared squared. Now remember this psi was phi and then plus log mod t squared e to the lambda, so phi plus v. So this term here is just e to the minus phi. Okay, so that means that the integral over omega j of alpha epsilon squared theta e to the minus psi dv sub g, that's equal to 1 over delta epsilon squared integral over omega j chi prime e to the v over epsilon squared squared f0 squared e to the minus phi times e to the v plus epsilon squared squared dv sub g. Okay, so I hope at least you believe that you can confirm these calculations later. I think if I can write them this fast, must be harder to follow. Oh, there's a 6 here. Okay, so now if you just you buy this formula, you notice that this chi is actually constant, outside, well, what am I saying? There's actually, the support of this is in e to the v less than epsilon squared. So actually, this is e to the v less than epsilon squared. So, or e to the v over 2 less than epsilon, okay? And then we can just get rid of this term and replace it by this, oh, and I missed a 4 from this 2. So there's 4, 1 plus ct squared. Okay? But then also this term can now be controlled. This e to the v is less than epsilon. So maybe my constants are wrong. Okay, I don't know. I mean, it could be 4 times 24 in the theorem. It doesn't matter as long as it's a constant. Okay, so let's just pretend that this is still 4 to make my proof work out. So if this is bounded by epsilon, 2 times epsilon squared, so I can bring that out, and this will be epsilon squared. Okay, and now you're in good shape, you see, because you have the integral of f0 over, so here's your z, you're integrating over some, this is supposed to follow z, some epsilon tubular neighborhood defined by these functions, dividing by the area of the tube. So in the limit as epsilon goes to 0, this is going to converge to the integral of little f, which is the extension of f0, right? But the volume form is going to do what I said when I was talking about adjunction. So what I'm saying is that for epsilon approximately 0, this is going to be less than or equal to 4 times 1 plus ct squared over delta times the integral in the L2 extension theorem. Okay, all right, so now this is finite, so we can apply Donnelly-Pfefferman. By Donnelly-Pfefferman, Osawa implies that there exists some u epsilon such that d blah, 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 right? Whatever the theorem says. So this equation here, okay? But the estimate is for u, right? Not for, okay. So now here's my extension. My extension is going to be a limit of the following things. F epsilon will be this e to the minus eta 1 plus a square root u epsilon minus f0 tilde, right? Or f, what did I call it? F epsilon tilde, the cutoff, right? This is holomorphic by the nature of the d-bar equation that's being satisfied, right? So this is a holomorphic section on omega j of the line bundle L along omega j. And what's its L2 norm? Okay, so this guy here is just supported on the picture I just partially erased, right? It's just supported in here, but it's just some smooth function. So as epsilon goes to 0, that's just going to disappear. All the estimates are going to come from this term. So this is and I should be writing omega j. Omega j, omega j. So this is going to be e to the minus eta times 1 plus a u epsilon squared e to the minus psi. When I put in psi instead of phi, I have to bring back some e to the minus v. E to the v. So e to the v minus eta if I want to have this be psi. Okay. And the point of choosing those functions was first to get this positivity of curvature, but second in such a way that this is bounded. And in fact, it's bounded by approximately 6, the way I had designed it. Okay. I should say that the function a was just chosen to optimize the form of the twisted curvature. But if you choose it more carefully, then you can get a sharp constant here. And there's actually a paper in the Annals published where all they did was choose this better function. Okay. So Jeff and I knew at the time that we were doing this that this was not optimal, but we didn't really want to delve into finding the optimal one because we had no reason to look for the optimal constant. In retrospect, that was probably an oversight. So, okay. And so if you put all this together, you get this the magical disappearing 4. Right? So if we forget about this 2, you get 4 times 6. The cross-sectional area is pi epsilon squared. So you get 24 pi over delta. So maybe it's 96 pi over delta. I don't know. That's the proof. So. Okay, I think it took longer partly because I spent a lot more time than I expected in the beginning on the adjunction, because people haven't seen it, so it's worth talking about. So sorry for going 15 minutes over. Okay, so now go get some coffee and I will put up some problems.